All right, I'm going to show you how to graph polynomials out of factored form and out of standard form. So I'm going to put this factored form into standard form because I think a lot of you could use a refresher on how that would even be done. It's going to take a long time, but I think it'll be worth it to do it once. All right, first let's get rid of these squareds and cubes over to the right here. Just put x plus 3, x plus 3, x minus 1, x minus 1, x minus 1. That way we can expand the binomials easier. Now these are all multiplied together, so it doesn't really matter what order you do it in. So I'm going to do a few at a time. I'm going to do x minus 5 times x plus 3, and at the same time I'm going to do x plus 3 times x minus 1, and at the same time I'm going to do x minus 1 times x minus 1, because multiplying a binomial by a binomial is quite easy. So we end up with negative 6x cubed, and then that's times x squared minus 2x minus 15, that's x minus 5 times x plus 3. Then that's times x squared plus 2x minus 3, that's these two combined. And that's times x squared minus 2x plus 1, that's these two combined. All right, here's where it's going to start getting ugly. I'm going to multiply this degree 2 polynomial with this degree 2 polynomial, and those two together are going to become a degree 4 polynomial, as you see. Now the way to do that, I'm going to say x squared times x squared, which is x to the power of 4, x squared times 2x, which is 2x cubed, x squared times negative 3, which is minus 3x squared, negative 2x times x squared, so minus 2x cubed, negative 2x times positive 2x, which is minus 4x squared, negative 2x times negative 3, which is positive 6x, negative 15 times x squared minus 15x squared, negative 15 times 2x minus 30x, negative 15 times negative 3, which is positive 45. You have to multiply each term in here by each term in here if you want to get the multiplication of those two trinomials. All right, we'll keep this x squared minus 2x plus 1 for now, and I will reduce this. So I got the 2x cubed, and I've got a negative 2x cubed. Those will cancel out. I've got a negative 3x squared, a negative 4x squared, and a negative 15x squared. So that's going to be negative 22x squared. Let's see, my x is 6x and negative 30x, so negative 24x. And I got my plus 45 and my x to the 4. And we still have my x squared minus 2x plus 1 that we have to multiply. Now we have a 4-term polynomial and a trinomial to multiply together. We're going to have to do x to the 4 times this one, times that one, and times that one. The second one times all three. The third one times all three. And the fourth one times all three. So we're actually going to have 12 operations that we have to do here. And then we'll simplify from there. X to the 4 times x squared is x to the 6. X to the 4 times negative 2x is minus 2x to the 5. Then you got plus x to the 4, minus 22x to the 4, plus 44x to the 3, minus 22x squared. Then you got minus 24x cubed, plus 48x squared, minus 24x, plus 45x squared, minus 90x, plus 45. All right, let's clean this up. We have an x to the 6. We have, let's see, the x to 5. So we got negative 2x to the 5. That's it. Okay. X to the 4. So we got 1 minus 22. So that's negative 21 so far. That's it. Minus 21. X to the 3. So we got 44 of them. Minus 24 x cubes. So 20 x cubes. Minus 22x squared plus 48x squared, so that's 26, plus 45, so 71x squared. Let's look for x. Minus 24x minus 90x, so negative 114x, and plus 45. All right, the last thing we have to do is this negative 6x cubed has to be multiplied by every single one of these terms. So negative 6x cubed times x to the 6. So you got negative 6x to the 9 plus 12x to the 8 plus 126x to the 7 minus 120x to the 6. got minus 426x to the 5 plus 684x to the 4 minus 270x to the 3. All right, now that took a lot of work. Now I actually don't expect, I do expect you guys could all do that. I just don't expect that you would take the time to do it every time. So that's not going to be one of the expectations, that you spend all that time expanding huge polynomials from factored form to your standard form. However, I want you to recognize that every single one of these steps is the exact same function in a different form. This is your standard form, this is your factored form, and these are all somewhere in between. They are factored in some way, but this is your totally factored form up here. So if I plugged in, let's say x is 2, here, 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 and here, and here, each one of them is going to give me the same value for y. Let's try it out. All right, so it's going to equal 3,600 for every single one of these equations. Now I'm just going to concern myself with the standard form and the factored form here. One interesting thing that might come out of this, negative 270 here, this last one, well, that is negative 6 times negative 5 times positive 3 times positive 3 again times negative 1 times negative 1 times negative 1. Interestingly, right? If you notice, that last number is always when you multiply the last number of each set of brackets. That's what comes out of it. And so when you multiply it all out, so it's also equal to negative 6 times negative 15 times negative 3 times 1. Or you could just say it's negative 6 times 45. It's like the last number in each one of the brackets. 45 times negative 6. 1 times 45 times negative 6. Right? That will always give you your last number here. So that could sometimes be helpful when you want to, let's say you're looking for the y-intercept and you're kind of looking for that last digit. That'll be helpful, that you don't have to go through the whole expansion to find it. To be honest, this probably wasn't the best equation to show you that with, because the y-intercept is just 0 in this case because of this x cubed. But if there wasn't an x cubed at the beginning here, then negative 6 times negative 5 times 3 times negative 1 would be the y-intercept, because you'd end up with just a negative 270 at the end, and all the other terms would just knock off when you put an x equals 0. Now I'm just going to do a table of values to kind of see what the graph of this would look like. Now I always like to start off with x equals 0. So let's plug in an x equals 0. And I'm just going to do the standard form right now, because I'm going to pretend that we don't know the factored form. We're going to learn how to factor these things from standard form, but let's just pretend we don't know the factored form for now. So when I plug in a 0, the answer is y equals 0. You can verify that on your calculator if you want. 0 is pretty easy because all of the x's equals 0, so every single term equals 0. But if you notice in the standard form, the y-intercept is always given. Now in this case, it's a little bit hidden, right? Because this is actually negative 6x to the 9 plus minus 270x to the power of 3 plus 0x to the power of 2 plus 0x plus 0. There's 3 terms that are missing here thanks to this x cubed here. But you still see that last term, the one with no x's, is 0. So that means the y-intercept is going to be 0. But if this standard form was actually continued and had like plus 3x squared minus 2x minus 4, well then the y-intercept would be negative 4, because every single one of these terms would equal 0 thanks to the x being 0. But this negative 4 would still stand. So it would be 0 minus 4, negative 4. So the standard form is awesome for finding the y-intercept. You know it right away. Now, besides that, the standard form doesn't really give a lot of hints of what the important numbers are, besides the fact that you might know because of this negative 6 and because of this x to the power of 9, you might know the end behaviors. But inside, when you're real tight in at 0, 1, 2, 3, 4, 5, -1, -2, -3, -4, -5. You really have to just plug in every single number to kind of find where it's at. So in standard, usually when it's in standard form, I don't bother doing a table of values. I actually put it into factored form, and then I could start putting in numbers that are significant. But the thing I want to talk about here with standard form is what does happen when you get numbers that are larger than these numbers that matter, the 5s and the -3s and the 1s. Like, what happens when it starts getting larger than that? So let's just check it out. Let's say, let's put in a 7, let's put in an 8, a 9, a 10, -7, -8, -9, -10, and let's evaluate by plugging it into the calculator the long way and see what happens. Now, the thing to notice here is you still have your coefficients for each term, but if you look at the x to the 9, the x to the 8, the x to the 7, the x to the 6, once I plug in the number, let's say I plug in a 10, well then this term, just the x to the 9 part, is 10 times as large as the x to the 8 part. And that is 10 times as large as x to the 7, which is 10 times as large as the x to the 6, which is 10 times as large as the x to the 5. So that means that 10, 100, 1,000, 10,000, the x to the 9 is 10,000 times as big as x to the 5. So even when you multiply the x to the 5 by 426, well, you'd have to multiply by 10,000 just to make it equal to 1 here. So this one would have to, this x to the 5 would have to be multiplied by 60,000 just to be equal to this 6. Right? So you can see how, and then if I put in 100 for x, like if I got way to the right, now this is 100 times, this is 100 times bigger than this one. This is going to be 10,000 times as big as that one. This is going to be a million times as big as this guy, and 100 million times more than the x to the 5. And so this coefficient here, just to make any difference whatsoever in this equation, would have to be like 600 million. Well, it's clear that it's only -426. Even if it was 600 million, well, I could just easily modify. I can say, well, this x value, I can make it even higher. So if I make this x value as high as I possibly can, then these leading coefficients are all going to be tiny compared to that x value. And these, even this x to the 8, x to the 7, x to the 6, x to the 5, x to the 4, x to the 3, those numbers are all going to be tiny compared to this x to the 9. Let me just give you an example. I'm going to give you x is 100. Now let's check out what this whole thing equals. All right, so when I let x equal 100, this is going to be -6 quintillion plus 120 quadrillion. Now keep in mind, this number here, 12 times 100 to the power of 8, that's a huge number, right? It's like 120 quadrillion. But what you have to understand is the number here that we had done of -6 quintillion is still 50 times larger than this 120 quadrillion. So that means, let's say this is 0 right here, and this is -6 quintillion. Well, the 120 quadrillion is only 1/50th of the way back up. Like, we went down this much, and we only have to go 1/50th of the way back up. So you can see here, it just went up a tiny little bit back up here, and that's 120 quadrillion. Now this third term here is 12 quadrillion 600 trillion. Again, that seems like such a huge number, but that now is only 1/476th of the way. So I actually moved this blue dot up a bit, but I only moved it up by 12 quadrillion 600 or 600 trillion. So that's such a small amount. You can't even notice it. Of course, we're comparing that to -6 quintillion. Now I think you guys can see where I'm going with this. This next term here is only 100th of that last term. So if that last term barely moved this at all, 1/100th of that is going to move it even less, right? And then this guy is only going to be much less than that, and much less than that, and much less than that. So yeah, it's not that these numbers aren't all that big. It's just that once you get even x is 100, the difference between each of these terms becomes so huge. Now imagine that you have x is 10,000. Well, now the difference, even after this first one, it's going to be this is going to be a -6 with like what do we got, like 36 zeros, and then the next one will only have 32 zeros. So it'll actually be just like a little particle up and down for each next term, right? So when I calculate this, you'll see that this number won't be all that different from -6 quintillion. So let's do the actual calculation. Put in 100, see what we get. All right, at x is 100, we get y is -5 quintillion, 867 quadrillion, 524 trillion, 191 billion, 870 million. As you can see, it's like really close to -6 quintillion, right? All these other terms made barely any difference, and that's only at x is 100. If you go to x is 1,000, well then this becomes even 10 times, like the difference that the other ones make is only 1/10 of that. And then as you go to like 1,000, a million, a billion, a trillion, a quadrillion, like these become so insignificant so fast. And the last thing to observe is that when you are putting in a really big number for x, well, really big number means x is positive. So x to the 9, no matter how big you make it, x to the 9 will always be positive, or x to any whole number will always be positive as long as you're putting in a positive number. But remember, this term is still being multiplied by -6. So yes, it's going to end up being -6 quintillion. So it's a really big negative number. And then as we saw, as x gets bigger and bigger, these guys become really not very significant. Like they barely change this number at all, right? So as you saw, it's still really close to -6 quintillion. And that's even, I mean, as you get higher, it gets even closer to the actual number. That's percentage-wise. So in summary, none of these terms matter when you start getting far to the right of your graph, or far to the left is the same issue. The only difference with the far left is you are putting a negative number in for x, so you have to be careful. If the degree of the polynomial or let's say the degree of the largest term is an even number, then this part of the term will be positive, and then you check to see, you multiply by whatever this part is. But if the highest degree is an odd number, well then that changes things, because when you plug a negative number in here, this whole thing stays negative because you multiply it an odd number of times, and then you multiply that by whatever this coefficient is, and it's going to be the negative of that. So that's why with odd numbers, when you plug in a large number or you plug in a small number, so when you plug in a really big number or a small, like a negative big number, you're going to get opposite effects. One will go really positive, the other one will go really negative, right? So when you have polynomials, you just check this. If it's an odd degree, you know you're either going to be really high on the right-hand side, that's if there's a positive coefficient, or you're going to be really, and if this is an odd degree, then it'll be really low on the other side. But if you have a negative coefficient, you're going to be really low over here and really high over on the left, right? Whereas if you have an even degree, well, you know that if you have a positive coefficient, you're going to be high, and if you have a negative coefficient, you're going to be really low and really low. All right, now in standard form, those are really the two things we're investigating. But at this point in the course, you should be able to just know that you're looking at this coefficient. If it's negative, then you know the graph is ending down. If it's positive, then you know that the graph is ending upward. And then if this is odd, you know that it's going to be the opposite on the other side. And if it's even, it's going to be the same on the other side. The other thing we want to look at is that last term. Well, here that last term is hidden because you should say plus 0x squared plus 0x plus 0. That last term is 0. And so that last term will give you the y-intercept, because when you plug in x is 0 for everything's going to fall off except for that last term. So graphing when it's in standard form isn't the most fun thing in the world. The only things you know are the end behaviors and the zeros. Sorry, I shouldn't say the zeros. You don't know the zeros. It's the end behaviors and the y-intercept. Now the factored form is going to give me a lot of hints at what x values are going to make me curious here. So I'm going to want to put an x equals 0 here because I know that, well, I know what's going to happen already, but that's going to make me curious. What about here? I'm going to put an x equals 5, an x equals -3, an x equals 1. Each one of these factors is kind of giving a hint as to numbers that would be really good in my table of values. But other things that make me curious are kind of like what happens in between these numbers, and then what happens to the right, and then what happens to the left. Oh, another one, you always want to plug in at x is 0 as well because you want to see what the y-intercept is. But to note, this -6 is also the leading coefficient when you're in factored form. So you have the same leading coefficient whether you're in standard form or in factored form. So you actually know the end behavior as well. Since this is negative, you know that it's going to end to the right. Now the degree is hidden, but it's actually really easy to find. In standard form, it's x to the 9. We know that. So we know that the degree is 9. But in factored form, when you expand it, you have to look. You have to see this x to the 3. That's 3 degrees already. When you multiply it by this, you're going to get an x to the 4 term. And when you multiply that, so you're going to have an x to the 4, by this one, you're going to have 2 more x's, so x to the 6. And then here, you're going to get 3 more factors, which are going to give you x to the 9. So each factor with an x in it is going to give you a higher degree. If you have an x squared in the factor, then that's going to give you 2 higher degrees. Let's say I had an x squared, and then that is cubed. Well, then that's going to give me 6. So it's like an x squared, another x squared, and another x squared. That's going to give me 6. It's going to add 6 to the degree. So you could actually really quickly see that this is of degree 1, 2, 3, 4, 5, 6, 7, 8, 9, degree 9. Since you know it's degree 9, now you know both end behaviors, right? -6 means it's ending down. And since it's degree 9, we know that the other side is going to be the opposite. So basically what I'm saying is the standard form is only good to find the y-intercept and the end behaviors. But the factored form, you can easily find the end behaviors. You could also easily find the y-intercept just by plugging in x is 0. And it's a little bit more work, but not a lot. And you also know all of your zeros. You also know all the x values that you can choose to make this thing equal to 0. If I let x equal 5, well, plug this into your calculator. -6x times 5 cubed times 5 minus 5 times 5 plus 3 squared times 5 minus 1 cubed. You'll see that it equals 0 because this term will equal 0. And then when you multiply 0 by other things, you get 0. So that's the beauty of factored form, is that each term or each part of this factored form could equal 0, which would make the entire thing equal to 0. And it's really easy to see what would make this equal 0. It's 1. It's -3. So factored form is the form you're always going to want to have if you want to graph a polynomial. So if I give it to you in factored form, graphing is going to be really easy. If I give it to you in standard form, you're really going to want to factor it. And that's what we're going to learn in Friday's class. Once you factor it, then it's going to be really easy to graph.